This is joint work with Hao-Jan Lee and Nicola Rente. My students, Li Gao is a former student, so this is part of their work. We actually from Illinois without an S, sorry to correct that. That's very important with any kind of French background, which if you're in Canada might actually be acceptable to be picky about. So let's talk about, why I'm interested in Ricci curvature. So there's some motivation. So if you go Ricci curvature and Riemannian manifolds, it has some impact on cohomology groups. Actually, strictly positive Ricci curvature implies that a cohomology H1 vanishes. So there's a connection between curvature and topology, and that is a classical object in commutative and non-commutative geometry. So this is a good sign that might be interesting. Ricci curvature is less understood. Sectional curvature is much better understood, but it's very important. Then the other motivation I have comes from concentration of measure phenomena. There's a very famous Talagon inequality, which is used in computer science, and the theory of optimal transfer developed by Sturm, Villani, the French politician, and so on. So there's a very exciting new perspective, understanding these concentration inequalities from a functional point of view, and that gives this theory a lot of new energy and actually really some new interesting directions. Particularly what they do is they go from the curvature of the space to the curvature of the state space. And curvature of states, that's something which is accessible to non-commutative perspective, right? Whereas the curvature on a space where you have no points is really hard to understand what that means. Good, so this is another motivation. Then there are these decay estimates in quantum information. You have something, no, I don't want to unmute myself, okay. I had to do this because I had an announcement I should unmute myself, but I don't want that because then there's a feedback. So the quantum information part is about decay estimate of certain dynamical systems, and think about you have some entanglement stored in a system and this decays over time. Well, then your entanglement is lost, but you have to know how much time you actually have to do any kind of non-local game, right? We heard how important non-local games are, but you can only do that in the first time interval before everything is returned to a classical scenario. So that's why we should know what these decay estimates are, even if they're hard to get. And then finally, yeah, you can ask much more complicated questions for non-commutative geometry. What is the moduli space? What is the space of parameterize, characterize all Riemannian metrics? That's beyond me, but you have to understand what are good and bad properties of Riemannian metrics if you want to know that. So maybe it's a good idea to go in this direction. So this is the classical motivation. For those who have not seen Riemann curvature before, I will give a definition now, which I have to do several clicks here. So our starting point is a manifold. Then we have a volume form and a metric. So these things are not independent. If you have the metric, you have a volume form, vice versa. But I want to stress that we have a space, a measure, or later on we will have a trace, and we have some inner product, right? So these are the data we are looking for. Then there is a Laplace-Beltrami operator, which is the sum of squares, right? Often this is written as summation minus xj squared of an orthonormal basis of vector fields, right? So that's the Laplace-Beltrami operator. So this is part of the data, and it comes from the metric. So this is part of the data which is induced. And then the Ricci curvature I'm interested in is this funny equation. So what am I doing here? The nabla is the map which sends smooth functions on the manifold into actually C infinity of T star of M. So we are sending a function to a differential form. And that is the differential operator. It's really the sum of these xj's, right? So we are collecting all the different orthogonal derivatives together. So this is the derivation. And if we apply the derivation to the Laplacian, we get another Laplacian applied to the derivation plus, right? So this is this, and plus a linear term or a scalar term. So the important is that this is order 0, right? I mean, that's the important thing. And this monster here is called rough Laplacian. Okay, and rough Laplacian is important because what you do is you have a certain bundle, and then you can do a trivial connection, and if you take this trivial connection, you get another Laplacian, and that's a rough Laplacian. So if you have never seen that, that's hard, but I want to just emphasize here that we have, you know, two connections here. One which is really better suited for the geometry, and one which is flat. And comparing these two makes everything work. But the important part here is that, you know, A hat, delta hat, is again a generator of a semigroup. And that will be the key remark for the following, right? So this is the funny thing. We are comparing delta, and then we have this generator outside plus the Ricci curvature. So this will be the key form, and people have looked at this for a long time. So this is not me first, there's work, but wow, Talmaya, Gong, they have looked for such kind of formulas for a long, long time. Okay, so just for the sake of completeness, I wrote down what the Ricci curvature is. You can express it in terms of the Riemann tensor, and you don't have to remember that formula. It's just something that you can actually write it down once you know what a connection is. And if you have never heard about the connection, that's fine for the rest of the talk. If you want to understand geometry, it's not fine. At some point, we have to address connections, but it's fine for what we're doing in the following. Good. So this is just as a matter of completeness. Wonderful. Are there questions so far?
Just a remark.
Yeah.
The line for 9, 6, that triangle should be in a different direction, right? It should be upside down.
This one?
9, 6.
Here?
9, 6. 9, 6. 1, 2, 3, 4, 5, 6. The rough Laplacian should be rough gradient. Yes.
You are absolutely right. This is somehow delta 0 star delta 0, and this was the flat one, right? The flat one, and the other one is the non-flat one. You're absolutely right. Yeah. Thank you. Good. Thanks for helping me correct my slides on the way. That's just incredible. So the non-convetive setup is trying to imitate this, right? So what we do need, we need some data. And so I will start with the finite von Neumann algebra. This is not super necessary, but it makes my life, 1,000 times easier. So I will do that. Then I will start with a semigroup, e to the minus delta, a semigroup on completely positive self-adjoint maps. I mean, we all have seen dynamical systems, and so this makes a lot of sense that maybe that is an important thing to consider. With such a semigroup, we get some data delivered, which is called the gradient form. So the gradient form, 2 times gamma of x is delta of x star y plus x star delta of y minus delta of x star y. So it sounds very funny the first time you see it. In many ways, it's somehow how far is a generator away from a derivation. It's an interesting expression. It's called carré du champ by Paul-André Mayer. It really is, in the classical case, gamma of xy is just inner product gradient x gradient y, and these here are functions, of course, not points, right? So it's an imitation of that, and this is how it works, and that's how you should understand it. This is defined for more elements than it looks like, right? So this delta x star y is a little bit problematic. It is defined for x in the domain of the generator delta 1/2. Okay, delta 1/2 intersection n. For those it's well defined. There's a lot of work of Sauvageau, Cipriani, who understood, okay, why is this working? And in fact, the key important thing which we have to understand is that we have this gradient form, or alternatively, we have a derivation. And the connection between the two is given like this. Gamma of xy is the conditional expectation delta of x star delta of y. And this conditional expectation replaces the inner product, what we have seen before. So this is conditional expectation. And of course, I will assume here in my setting that this derivation sends the algebra of smooth functions into a larger finite von Neumann algebra containing the original one. So I have this finite von Neumann algebra floating around all the time, and that is the setting which helps me. Do I explain how that works? Yeah, I will explain how that works in the classical case in a moment, but I first want to make the connection to non-convex geometry.
We have a question in the chat. Is
okay.
Cal A an algebra?
Actually, absolutely. The script A is the set of all elements x in N, so that delta of x to norm is finite. And that turns out to be a star algebra. And that's very tricky, but it's true. Right? I mean, a derivation is always, you see, you have to, so you do something like delta of x times y is delta of x times y plus x times delta of y. That's the Leibniz rule. And so if this is an L2 and this is bounded, and if this is bounded and this is L2, then it's again bounded. So the algebra property comes from the derivation. And the whole theory here between the things is to figure out what is the right algebra to work with. But this took a while. This is it's a very good question. It's actually one of these questions where you have to be careful. Did that answer that? Okay, good. So connection to non-curvature geometry. Non-curvature geometry is given by spectral triple. A spectral triple is given by some algebra, some operator, and then an inclusion of A into some bounded Hilbert space, right? And the derivation is just given by this commutator. That's the link, right? So for a spectral triple always gives you a derivation. Now, what you don't know is whether this derivation is contained in a finite von Neumann algebra, but there is something more important, and this is this universal bimodule of differential forms. So this is literally defined in Kahn's big non-curvature geometry paper, so we can abstractly define what the derivation is. It sits in the tensor product of A tensor A, where delta, the universal one of A, is A tensor 1 minus 1 tensor A. So this is kind of a universal derivation. And then you make it a right module, and by the derivation properties, automatically a bimodule. So this is in Kahn's book. If you've never seen it before, it is actually just 5 lines, well written. And you don't have to read the whole book. That's a good thing. So there's a universal object of differential forms. And whenever you have a derivation, you have a representation of that bimodule in the bounded operators on H. And that is really simply given by what you want it to be, right? So by pi delta of A tensor 1 minus 1 tensor A is delta of A. And then the representation of the module here will send summation delta bullet AJ BJ to summation delta of AJ BJ. So you're just replacing the universal representation with this concrete derivation, and then you have a bimodule representation. And what you think of this is that these are the concrete differential forms which you get from a concrete derivation, right? So we have now some bimodule of differential forms, and that will be the object we care about. And then, so the remark is, if you have a spectral triple so that the space of derivations is contained in a finite norm von Neumann algebra, and there's a conditional expectation, and this, if you calculate this here, you get back the generator, then you have also a generator of a semigroup. So there is some back and forth between a spectral triple and the notion of derivations, which we will consider here. Good. Yeah, so let me give you the definition of differential triple, which I created, following this this kind of inspiration by Kahn. So I give myself a von Neumann algebra N, a finite, a derivation, and an inclusion delta in N. And I'm assuming that this derivation on some nice subalgebra, weakly dense subalgebra, is a derivation, has dense domain. And this inclusion is tracial. So this is my definition of differential triple. It differs from the one before, that I'm not specifying the D, right? I'm just working with the derivation, but I'm asking more in that I'm asking that the derivation sends me into a finite von Neumann algebra. And I have a conditional expectation. So it's a little bit more and a little bit less compared to Kahn's theory. So that's just what I said here, right? So I'm replacing this here by this derivation, that's all. And then I can say abstractly that a certain differential triple admits a curvature operator if there exists a generator delta hat on the larger algebra and an NN bimodule map, which I call Ricci, by analogy, so that I have this equation holding. The derivation applied to the Laplacian is the new Laplacian applied to the derivation, plus the Ricci curvature operator applied to derivation. So this is the key property, But I have another requirement, namely if I restrict the new, this is important, right? So this correction here, please note, if I take the new, oh, now it's gone. So the new generator restricted to the algebra is the old generator, right? So there are two conditions, is this Ricci curvature condition and this restriction condition. And these two together, they will allow me to say that I have a Ricci curvature operator. And then I say that my Ricci curvature operator is bounded from below by kappa if this Ricci curvature operator is bigger than kappa times identity actually on P delta of omega bullet of A. So I don't need this globally. I only need this on the space of differential forms, right? So I haven't said that exactly, but this is actually what I really need. Usually it's not globally satisfied. Then of course I want to have that this spectral, this differential triple induces my semigroup, and that is the second condition. So I'm literally taking the definition from the commutative case and reformulate them in terms of operator algebras. But I insist that I need this larger algebra. And I think I'm telling you now why this is actually really natural in the commutative case. In fact, in the commutative case, you can take for M the Clifford algebra in n variables, and the derivation is given in that form. And then everything works out just fine, right? So then the Ricci curvature coincides with the one we had before. If you do this for the space L infinity 0, 1, you can calculate the optimal Ricci curvature turns out to be 1/2. Identity minus E is a weird generator, super non-smooth, but that doesn't change a thing. Good, so I see.
You just went mute for me, Marius.
Algebras trace roll up row. We introduce relative entropy, trace row, that's rho given sigma, trace row log rho minus trace row log sigma. That this actually makes sense is a complete mystery, but I want you to accept that. And then I will give you, I think I have to skip this synthetic theory of metric measure spaces in the commutative space because I will run short of time. I can come back to this in a little bit. So let me state the main results. Right, here it is. So this is our main result. It is a complete version of a theorem by Bakri and Emery. And what we prove is that if we have a lower bound on the Ricci curvature, then we also have this decay estimate for the entropy with the factor e to minus 2 kappa tau. So Ricci curvature below implies that entropy decays. And the Bakri-Emery theorem, the one which is classical, proved that exactly before. So let me do some remarks so that we have an understanding what's going on. So the classical Bakri-Emery theorem stated this for, we have a manifold and we have a volume and we have a G. And then they proved this for that, they proved that the entropy of TT rho, or the relative entropy of 1, goes like e to the minus tau kappa t, the entropy of the original state given 1. So this is some kind of entropy estimate. But what I should mention is that their proof will not even work for matrix value functions. So the classical proof they works for literally functions, they're using commutativity of their functions. So even if you want to extend the classical theorem to the matrix valued case, you have to do some non-primitive geometry. In fact, our proof uses a trick. It uses Lieb's concavity result for completely positive maps. And this result is so general that it actually extends to the matrix valued case, and it really extends to the operator algebra case whatsoever. So this is just great. Now let me just make a remark. So so this work of Sturm, Otto, Villani, what they have is they show that if the Ricci curvature is bigger than kappa, if and only if there is some convexity property on the state space, right? So they show that a certain functional is convex on the state space with respect to the famous Wasserstein-2 metric, right? And if you have not seen this before, I think it's better, you know, since I have only a couple of minutes left, it's better I give you the big picture. By the way, I will put the slides, a link to the slides in the chat just after I'm finished, and then you can read the full slides as well. So I can prepare that, but not while talking. So after I'm done with the talk, I can immediately put this in the chat. So the idea is now that coming from quantum information theory, they, you know, the work of Carlin and Maas, they extended this to, they have a notion of Wasserstein distance. And what we prove is that using, you know, results by Carlin and Maas plus us, we can also prove that the Ricci curvature bound in our sense implies the same convexity properties. So this entropy estimate is just, you know, the top of the iceberg of some better understanding of geometry of spaces. Yeah. So that's really the plan which we had laid out. So now let me go to, you know, since I'm running low of time, let me go to my favorite example, which is here. So at the end of the day, you also have to understand one example well. And what we do is we take the 3-sphere, and in the 3-sphere, you have 3 directions, right? Look at the North Pole, you have 3 directions, but we differentiate only in 2 out of 3. And then we look at this differential operator, which differentiates, here's a minus, in fact. And then we observe, or we prove, that the Ricci curvature in our generalized sense of that operator is bigger than kappa if and only if the number operator on the 2x2 matrix algebras has Ricci curvature bigger than kappa. And the number operator, this is the number operator. You have the x, y, z matrices, right? You know, your x is this one, y is this one, and z is this one. And you know, the fact that I'm using x and y and that these letters coincide is not a coincidence. It actually, you know, it is really transferred over. And so we show that Ricci curvature below of these 2 objects, the infinite dimensional 3-sphere with 2 out of 3 direction, and the finite dimensional system, again with 2 out of 3 directions, they have the same Ricci curvature bound. And then we are actually able to calculate that. And we see that the Ricci curvature bound is exactly 1, and the CLSI bound, the complete decay bound, is 2, and that's best possible in all cases. Now, the point is, for this guy, before even the commutative decay estimate was not known, at least not precisely, and we have the optimal value here. So it is so that this non-commutative understanding even allows us to understand certain commutative systems a little bit better than before. So that's probably a good point to finish. And if you want to know more about this anti-transference result, here is a talk from Wednesday. Then I want to thank you for listening, and really want to thank this organization team, because I find it amazing that they took this effort on them to let us, you know, come together. Thanks a lot.